Hi, welcome to the third and last session of Algebra 1 course. This is the last live session, and this live session is going to be for 1 hour live session. So, in this live session, mm, we are going to discuss as per continuation. That is, in last session, we were doing tensor product, but in last session, it was not completed fully because I decided to do some problems because I feel that tensor product is something quite not easy thing for first time. That's why today we shall go with the test product, and if the time permit, then we shall go with the we shall go with then other portion. So I mean we shall go with the repetitions. Okay. So first we shall go with the test product. Okay. So so okay. So the first question. Okay. So I think it's good to recall also things. So recall some properties. So those properties are namely, suppose M and N are both R modules. Okay. Then we have M1 plus M2 tensor small n is equal to M1 tensor small n plus N2 tensor small n. Secondly, similarly, M tensor N1 plus N2 is equal to M tensor N1 M tensor N2. A x tensor y is equal to a into x tensor y, which is again equal to, sorry, which is again equal to x tensor ay. Okay, so these are some basic properties of tensor product. Okay, okay, so okay, so right now I'm not writing those why m on m belongs to, because I think you were smart enough to understand why a x y m n lies. Okay, so let's solve the problems. So suppose the first question. So right now these problems I'm taking from the book Hungerford Algebra. Okay. Okay. So hi, can you hear me properly?
Yes, sir. We have received mail. There was mentioned tomorrow session will be conducted in tomorrow, but today 19.
Today is 20. I mean, sorry, I don't get you actually.
Yes.
I don't get you. What is the problem?
Oh, okay. It is the last class, or tomorrow is another session will be taken.
One second. One second. Let me check the email once.
Yes, yes.
Today is Friday, right? So in Friday also, today Friday there was a class, right? Today
Mm,
from 4 to 6 p.m.
mm.
I mean, I'm not sure since it is taken by some other person. Maybe today is the last class. But I,
Is it?
properly I don't know actually.
This is your last session, okay?
Today it is my last session.
Okay. And then, another teacher is taking the update from that side, okay?
Yeah, correct, correct. Okay, so by the way, can you see the screen?
Yes, yes, yes.
Okay, and is there any noise in my audio?
No,
Okay, I mean yes or no? Yes or no?
no, there are no noise.
Okay. So okay, so the thing is that um, so on the last session we are going with the tensor product, right? So
Yes.
today also first we finish the tensor product and then if time permits we'll go in some other portions. Okay. So
Okay.
actually today I have decided to solve some problems from the tensor product, and right now I am the problems I'm taking from the book Hungerford.
Okay.
Hungerford Algebra. It is a book of GTM. Okay.
Okay.
Okay. So first problem is as follows. Okay, let. By the way, tell me one thing. Suppose you have an abelian group. Okay.
Hmm.
So tell me. So abelian group is obviously a module over something. So what is that? I mean, abelian group can be given an obvious model structure. What is that? Do you understand? Do you understand my question?
Yes, yes.
Yeah. So don't hesitate.
Uh, on onto itself.
No, no. It's, look, the thing is that suppose M is an R module means what? The R is a ring, right?
Yeah.
But group might not be ring, correct?
Hmm.
So I mean, so it does not make sense that it is a model onto itself. It does not make sense, right?
Hmm.
So think about and tell me. Abelian group can be given an obvious model structure. What is that? So the thing is abelian group, right? So this implies what? We already have a multiplication with z, right?
Hmm.
That is z cross something. So z cross g to g, correct? And
Yes.
the multiplication, the way it is, I mean, n comma g goes to ng. I mean, g plus n time composition. So this multiplication, I mean, satisfies those conditions of being a module, right? Correct.
Hmm. Yes, yes.
So any abelian group is a Z module. Do you understand?
Yes, sir.
Okay. Okay. So the question is as follows. Okay, I mean, coming back to the main tensor question. So if, by the way, do you know what does it mean by torsion group?
No, torsion. We have solved some problem. using this definition only in the field extension portion.
I mean,
Sorry, in module section.
okay.
Only tor something annihilator. It is related.
No, no. So tell me, suppose suppose it is given that G is a torsion abelian group. Then what does it mean? Then what does it mean by torsion? We tell me. Does it mean by torsion?
Torsion question is what is torsion group?
Suppose you have given that G is a torsion abelian group. Okay, then
Okay.
what does this mean?
Um, every element of finite order.
I mean, you told that you know this, so tell me the answer. If you tell that you don't, then I will tell you. I mean, also you have mentioned that you have done to plot things, right? So it is expected that you know the definition. Then, so you told that you have done the top. So what does it mean by torem? Hmm? What does it mean by torem? I mean, there is no point of being silent. Okay. So the thing is GBM torsion abelian group. It means that if in for every element A inside G, there is a natural number A inside N such that N is equal to 0. Okay. So this is by torsion group. That is every element. So I mean, so that is every element is a finite order. Okay. This is what it means. So now coming to the actual question now. The question is, let G be a torsion. Sorry, torsionability. Then show that G tensor Q equal to 0. G is a torsion abelian group. Now show that G tensor Q is equal to 0. Now let's try this problem for a couple of minutes.
Sir, one interruption.
Yeah, yeah, please.
Sir, actually, I'm Nimi. I had asked for the solution for the assignments. I couldn't attend the last session, so are they solved?
They are solved after, but after this tensor product thing, I will go to this only. Okay.
Which one, sir?
After finishing this tensor products
Uh,
problems, then I will go with those assignments. Okay.
okay, I had listed the questions in the portal, so it will be good if we can solve those questions.
Yeah, I mean, I will solve on the live session itself. Okay.
Which
After
one, sir?
finishing, I
Ah,
will
yes,
solve.
that's fine.
Yeah. Okay. Yeah. So tell me this question. Let G be a torsion abelian group. Anybody? How to solve this? Okay. So, so this type problem can be solved in a quite tricky way. So we have given G tensor Q. I mean, we need to show that G tensor Q is equal to 0, right? So now since G tensor Q, I mean, since M tensor N, these are generated by the elements of the form M tensor N. So only need to check G tensor P by Q is equal to 0 for all G in G and for all P by Q belongs to Q. Now, so take AG. So we will have some answer that in G is equal to, correct? Now G tensor P by Q can be written as follows. G tensor N P by N Q. Okay. Now we can keep put this N on its G due to this property. So this is the Ng tensor P by NQ and Ng equal to 0. So the whole thing becomes 0. So this tells that for any type of any generator of G tensor Q is equal to 0. Okay. So that's why this whole tensor product is 0. So do you understand the solution? Or do you understand solution?
Yes, it is obvious. Okay.
So now prove that Q tensor Q isomorphic to Q as 0. Please try this. Please attempt to solve this question. Are you getting any idea how to solve it? Okay, so this argument goes as follows. So first, what we need to first we need to make a bilinear map from Q cross Q to Q, right? Okay. So what is the map? The map is an obvious way. That is I mean Q1, Q2 goes to Q1, Q2. Okay. Now, obviously binary. So this gives a well-defined linear map from Q to Q, name given by Q1 tends to Q2 goes to Q1, Q2. Okay. Now, what are the reverse map? There is Q to Q tends to Q. What is the map? Q goes to 1 tends to Q. Okay. Now, do note one thing that this tells what this tells. I mean, if it F and G, then obviously what is G compose F? G compose F of Q1 is Q2 is equal to Q1 Q2 is equal to 1 tensor Q1 Q2. Now there is a trick. The point is this tensor are taken over Z. Okay. So basically you can't put it here directly, correct? I mean you can't separate Q. I mean you can't put the Q from one side to other side. So that's why, yeah. So that here the technique is that you need to write it down Q in explicitly, I mean in rational number form. Now you need to keep these things separately to the left. Okay. Namely, so M1 tensor 1 by N1, M2 by N2, and then this thing can be written as m1 by n1 into n1 tensor 1 by n1 m2 by n. This now I am taking this part here. So this is equal to m1 by n1 into n1 by n1 into m2 by n. So this is nothing but equal to m1 by n1 tensor m2 by n2. And this is nothing but q1 tensor q2. Okay. So this is our root. When do you
Sir,
understand?
scroll up.
Yeah.
Scroll
Tell
up.
me. Tell me. Do you understand it?
Yes, I'm seeing.
Yeah.
In case of reverse map, Q tensor Q to Q, there is a map Q1 tensor Q2 goes to Q1 Q2 and G G where come or where come from where come G.
Oh, I mean, you are asking in this direction G composes, or you are asking in the reverse direction?
Yes, reverse direction Q tensor Q to Q. There was a obvious map Q1 Q2 goes to Q1 Q2. Sorry Q1 Q1 Q2 goes to Q1 Q2 into G.
Basically, this is nothing but one tensor Q1 Q, one tensor Q1 Q2, right? Correct.
Yes.
Now the point is that up to this, so this is exactly G compose F of Q1 tensor Q2, correct?
Hmm.
Now from this portion, if you need to, you need to show this is equal to Q1 tensor Q2, right?
Yes.
So for doing that, we can't directly put. For doing that, that trick is involved here that we have just seen, right?
Yes.
Possibly, I could not understand your question properly. Can you please repeat your question?
Yes. My question is just scroll up. Uh, yes. Yes. Here the point is Q1 Q2 just before Q tensor Q to Q
Hmm.
a function f, and this form of the function Q1 tensor Q2 goes to Q1 Q2 into G. Sorry, G is the below function, Q2 Q tensor Q. Okay.
Yeah.
Okay.
And similarly, in the reverse direction, the map is f FGQ, which is nothing but f of one tensor Q, and it is equal to 1 cross Q. So this is equal to what? It's equal to Q, obviously. Understand?
Hmm.
Okay. So, so this is one. So one question. So okay, now tell me the last problem of the tensor product. So this is Q 10 Q by Z tensor Q by Z over Z is equal to what, and Q by Z tensor Q by Z, and tensor is taken over Q by Z is equal to what? 0 or isomorphic to something, those things. Tell me. Think about it and tell me. Tell me. Okay, so the one goes follows. Look, so we are in Q by Z. So first question. So any element look like P by Q plus Z tensor P1 Q1 P2. That's it, correct. So this is the general common element. Correct. So what you can do? Um, so you can multiply by Q2 on this side. Okay, right, separately Q1 bar Q1 bar tensor P2 Q2 whole bar. This is equal to Q2 P1 by Q1 Q2 1 P2 Q2 whole bar. Okay, now this is equal to this Q2 can you put right side because Q2 belongs to Z. So P1 by Q1 Q2 whole bar tensor P2 bar. But P2 bar is nothing but equal to U. So the whole tensor product is equal to 0. So that's why this thing is fully equal to 0. Okay, so these are
Sir, here something logic, not getting the logic properly. Scroll up,
yeah,
please. Scroll, yes, scroll up again. Oh, sorry, sorry. Scroll down, scroll down. Okay. And first component P1 by Q1 into Q2 into P2 by Q2 product. These steps
yeah.
from third step.
This right,
It is
this portion right.
both are multiplied, denominator and numerator. Okay,
Yes,
okay.
yes, yes, yes,
Okay,
correct.
okay.
Okay, now since also, I mean, so anyway, so this is one problem, and try this problem by yourself. And this has already been done in the first
Okay,
class
okay.
test report by different way. Also, we are running out of time, so now let's get into hard problems. So, so the first problem number was one second. Yeah. Okay, so let's start with I mean, Jordan canonical form. So this question is so given that the matrix has Jordan canonical form like this. So now the question is how to obtain rational capital. So this is the question. So first of all, as per the construction, okay. So first of all, Jordan canonical form matrix are the block matrices. Okay. So observe that Okay, so observe that this is one block. Okay, and this we know the last block always corresponds to what corresponds to that minimal polynomial, and it is only there is only one, no other. I mean, it is zero, it is zero. So the minimal polynomial is x minus one. Okay. Also observe that this portion consists of makes another block. Okay? So due to this portion, the invariant factor is x minus 0 whole cube, that is x cube. Sorry, x cube is invariant factor. So thing is what we have the x cube as invariant factor x minus 1. So and x minus 1 mere polynomial is all, so it's already an invariant factor. Okay, sorry, it's my mistake here. Only one is, yeah, there is one is there, right? So x minus 1 is mere polynomial, and x cube is one invariant factor. So from this, I mean, so these are, so now using this, try to get the rational canonical form. I mean, we have the list of factors. So from this, now it is obvious to get the rational canonical form. Also, one thing to note is that, I mean, this is what we are backtracking it, but the thing is, I mean, Jordan canonical form is a similar matrix. That is, for any matrix, the Jordan canonical form is similar with that matrix, right? So, and for any two similar matrices, the rational canonical form are also exactly equal. Okay, so you can directly go with the calculating the rational canonical form of this given Jordan form. So then also you will get the answer. Okay, but the thing is, this way of backtracking is more than efficient because you are directly getting the inverse factor and mere polynomial due to the construction of Jordan canonical form. Okay. Right now, I'm not doing the calculation because we are running out of time. So kindly calculate it by yourself. But this is the list of factors we're getting, and using this, we can get the
Sir,
rational
what
calculation.
invariant factor of the bigger block x cube minus 0, I mean x cube,
Yeah,
and set of invariant factor is x minus 1 and x cube. Okay.
yeah. So we have the set of factors right now.
Yes.
So using this, you can construct the rational canonical form, right?
Yes. Yes. Okay.
Yeah. Okay. So the next question is question number 15. So the question is, how many similarity classes are there in how many similarity classes are there the which satisfies the square equal. Okay. So how to solve this problem? So a square equal to a, right? So I mean, so a satisfies the polynomial x into x minus one. Okay.
Yes.
Yeah. So and similarity classes, the matrix are in from M to C. Okay.
Hmm.
And so I mean, Anyway, so since the matrix satisfies this thing, so minimal polynomial of A
Must
satisfies
divide.
minimal polynomial divides x or x into x minus 1, right? So the minimal polynomial can be whole x into x minus A, or minimal polynomial can be whole of x, or
Yeah.
minimal polynomial can be only x minus 1, correct?
Okay.
Now, if the minimal polynomial is x into x minus 1, so what are the list of invariant factors? Invariant factors are x into x minus 1. If the minimal polynomial is x, then what are the list of the invariant factors? X and x square. I mean
Yeah.
x and x, because invariant factor will divide the minimal polynomial, and product of all those factors is equal to characteristic polynomial. And minimal polynomial is 0, so characteristic polynomial has to be, I mean, roots of the characteristic polynomial is the root of minimal polynomial. So its characteristic polynomial x square, and so the other invariant factor is x and x. Okay, and similarly, if the minimal polynomial x minus 1, so the factors is x into x minus 1. Okay, so we have three possible answers, so the answer is 3. Do you understand?
Yes. Yes.
Okay, so now go back to going to the question number 12. One second. So the matrix A is given as 3 1 0 0 0 3. Now the question is, this belongs to M for Q. Okay. Then M suffix A is isomorphic to which other chord? Qt by. Okay, anyway, I am not writing down the full question because it will take time, more time. Okay, so I hope you have the question here by yours. Okay, so the question is, so there are some four possible answers. Now, question, how do you determine that? Okay, so first of all, observe that so for in order to answer the question, you need to go with the solutions. Sorry, the proof construction related to Jordan canonical form. Okay, and here you will observe that we have something. I mean, we have some form like fx by x minus alpha cube plus direct sum fx by x minus beta cube, something like that. Okay, observe that these are nothing but the invariant factors. So basically, in order to answer the question, you need to understand what are the invariant factors of this matrix. If you understand invariant factor of this matrix, then you are done. And suppose the invariant factors are, suppose A and B and C. Suppose, so the answer will be qx by A plus qx by B plus qx by C, something like that. Okay, do you understand?
Uh, yeah. Sir, please repeat on.
Yes. So basically, the thing is that in order to answer the question, you need to calculate the invariant factors of the given question. Okay. Now
Yeah.
you may ask why. The thing is, the answer is that you need to, for this, you need to go through the proof construction of the Jordan canonical form, how they're coming. Okay. If you go through the book, you understand that qx by those things are nothing but the invariant factors. So only you need to calculate the invariant factors. So for example, the invariant factors, if the invariant factors are x minus 1, x minus 2, x minus 3, then the answer will be qx by first invariant factor, qx by second invariant factor, qx the third invariant factor. Okay. I mean, you need just questioning out those invariant factor inside qx. That's all. Okay. So that is the answer. Okay.
Yeah.
That's it. So now question number 9. So given matrix J is equal to 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0. Now question is what is the dimension A, 5, M, 6 of A, J. Okay. So just tell me how we will approach this problem. I mean, how we will approach this problem? Tell me.
Yes, thinking. Okay, sir. On X 1 second, it is a dimension from the collection of those matrix, those commute with J. Okay,
Is a divergence thing? I don't get it. What is that?
dimension.
Oh, yeah, yeah.
Yes, dimension of those collection of those matrices which commute with J. Yes. There is any relation between eigenvalue and dimension?
So, I mean,
I,
why thinking so complicated about it?
okay.
So, look, the thing is that you have the given relation, right? A is equal to A, correct? So, this big equation. Now, from this big equation, if you multiply, then we will get some kind of relation. Namely, uh, please do the multiplication. I mean, thing is, we get first kind of some kind of relation between A, B, C, D, E, F, G, H, those things, okay? And using relation, you only get the answer. I mean, no need to think about dimension. I mean, about eigenvalues, eigenvectors. This will not going to help here. Only you need to use this equation and you get some relation definitely. During time cost, I'm not going to do the multiplication, but the technique is do the multiplication and you will get some relations between ABCD and up to PQ. Okay, and from that you need to get the answer. Okay, that's the only thing you need to do in this problem. Understand? Nothing more than that. Understand?
Yes.
Yeah. So, question number. What is CA? Can you please tell?
Yes. What is?
CA for any matrix A.
Yes.
What is CA? I could not remember actually.
Characteristic. No.
Oh yes, I can. So basically, CA consists of those matrix for which this relation. I mean, the set of all fixed elements of Z2 which are fixed by the matrix say after the multiplication. This is all represented by CA. Okay, correct. So now the question is, for which of the following matrices the Z by CA is finite? This is what you need to do. So first answer is given 3 2 3 2, and now we need to check Mn is equal to Mn for which Mn. Okay. So this implies what? So it just do the multiplication. 2m plus 3n is equal to m. 3m plus 2n is equal to m. So this implies what? This implies m plus 3n equal to 0, and this implies what? This implies 3m plus 8 equal to 0. Correct?
Yes.
Now, using this relation, you will get some certain values of m and some specific value of n. Correct? So Z2 by collection of those mn's is a singleton set. So it is obviously infinite for this first matrix. I mean, so technique is you will get either a particular value of Mn for any particular matrix A, or you will get some relation between M and N where we can't determine where the infinite many values may come. So in that type of situation, it will come finite. Okay. So for example, it's given, suppose if we take A to be 2662. Okay. So this is what 2m. So this is m plus 6n 0, 6m plus n. Now you can calculate m and n, and you will get the answer. Okay. I mean, either you will get infinite values of m or you will get finite values. In case of infinite value, you will get the answer. That's all. No. Okay. And similarly, the question one, yeah, similar to the problem number one can be solved. So, okay, so I'm not going to solve the problem one because it is exactly similar with the problem number two. Okay. One second. Okay, so as per Rimi's request, I have solved all the question except the question number one because the question number one is exactly same as question number two. Okay, so now tell me, now go back to the tensor product thing. Now tell me, we have some integer of type. Tell me this. So the QZ tensor QZ over Z is 0. So whatever the QZ tensor QZ over, I mean Q by Z over Q by Z over tensor taking over Q by Z. What is the answer? Just look at the question and think about it, because we are doing the same ring over itself as a module. Okay, so and we have also done one theorem in second last session.
It is q by
Yeah,
it
correct,
is
correct. Yes, this cubers. Very nice. Okay, so we have now Also try one problem in when you're free, not today. R is a ring and B is an R module. Show that this is isomorphic to B by I. You can try by yourself.
Please repeat the question.
Yeah, suppose B is an R module, then
Suppose.
show. Yeah, B is an R module.
Yes.
Now try to solve that R by I tensor B isomorphic to B by I. So try this by yourself. Okay.
B by IB.
Yeah, yeah. You understand the question? You understand the question? Okay, I will understand. Okay, so that's all for today. All the best for your upcoming exams. So I am going to end the session. So if you have any doubt, you can ask me. So you will have reply. Okay. Okay, I'm leaving the call.
Yes, sir. Whatever doubt, how can I ask?
Uh, drop an email.
Yes.
Drop an email.
Email. Where is the email?
I mean, that discussion forum, right?
Yes, yes. Sir, I have a personal question. Uh,
Yes.
you have told that you are in second year PhD. So, can you, besides from this academic field, can you